Every planet in our solar system spins like a top, rotating around an axis that points roughly up and down relative to its orbit around the Sun. Every planet except one. Uranus doesn't spin like a top, it rolls, like a ball someone kicked across the solar system and forgot about. Its axis is tilted 98 degrees, almost completely sideways. If Earth spun like Uranus, we'd have 6 months of continuous daylight, followed by 6 months of complete darkness. The sun would rise in the north, set in the south, and the seasons would be apocalyptic. Something catastrophic happened to Uranus. Something that knocked an entire planet onto its side and left it rolling through space for 4 billion years. And here's the thing that keeps planetary scientists up at night. We still don't know exactly what. Was it a single massive impact? 2 impacts? A gravitational dance with a moon that no longer exists? The answer might rewrite our understanding of how the solar system formed and how violent our cosmic neighborhood really was. Today, we're going to explore the strangest planet in our solar system, a world of extremes that defies explanation. A planet with seasons that last 42 years, a magnetic field that makes no sense, rings that stand on end, and moons named after Shakespeare characters that orbit in ways that shouldn't be possible. This is the story of Uranus, and I promise you, by the end of this video, you'll never think about our solar system the same way again. Let's start with a question. What do we actually know about this bizarre world? Uranus is the 7th planet from the Sun, orbiting at an average distance of about 2.9 billion kilometers. That's 19 times farther from the Sun than Earth. If you could drive a car to Uranus at highway speed, it would take over 3,000 years. Let me put that distance another way. When you look at Uranus through a telescope, you're not seeing it as it is right now. Light takes about 2 hours and 40 minutes to travel from Uranus to Earth. The image in your eyepiece shows Uranus as it was nearly 3 hours ago. If the planet exploded right now, you wouldn't know about it until dinner time. At that distance, sunlight takes about 2 hours and 40 minutes to arrive. And when it does, it's only about 1/400th as bright as what we experience on Earth. Imagine the dimmest twilight you've ever seen, and then make it hundreds of times dimmer. That's high noon on Uranus. It's cold out there, brutally, incomprehensibly cold. The effective temperature at Uranus's cloud tops is around -224 degrees Celsius. That's colder than liquid nitrogen, colder than any naturally occurring place on Earth has ever been. One of the coldest planetary atmospheres in the entire solar system. The planet itself is huge by terrestrial standards, but modest compared to the gas giants. Uranus has a diameter of about 51,000 kilometers, roughly 4 times that of Earth. You could fit 63 Earths inside it. If Earth were a golf ball, Uranus would be a basketball. But here's something most people don't realize. Uranus isn't a gas giant like Jupiter or Saturn. It belongs to a different category entirely. Planetary scientists call it an ice giant. This distinction matters more than you might think. Jupiter and Saturn are mostly hydrogen and helium, like failed stars that never quite gathered enough mass to ignite fusion. They're basically giant balls of the lightest elements, with small, rocky cores buried deep beneath thousands of kilometers of compressed gas. Uranus is different. It has a hydrogen and helium atmosphere, yes, but that atmosphere is just a thin shell. The bulk of Uranus is made of heavier stuff: water, ammonia, and methane in various exotic states. Not ice in the everyday sense of frozen water cubes, but what planetary scientists call ices, compounds that were frozen solid in the frigid outer solar system when the planets formed 4.5 billion years ago. Deep inside Uranus, these ices exist under pressures so extreme that they behave in ways that would seem like science fiction. Consider water. On Earth, water is a simple molecule, two hydrogens bonded to an oxygen. It freezes into ice, melts into liquid, boils into steam. We understand it completely. But crush water under millions of atmospheres of pressure and heat it to thousands of degrees, and something strange happens. The water molecules dissociate. The oxygen atoms, heavier and slower, lock into a crystalline lattice, a solid structure. But the hydrogen atoms, lighter and more energetic, flow freely through this lattice like a liquid. This is called superionic water. It's simultaneously a solid and a liquid, a crystal that conducts electricity like a metal. A state of matter so exotic that scientists only recently confirmed it exists in laboratory conditions. And there might be an ocean of it inside Uranus, thousands of kilometers deep. A sea of superionic water, compressed by the weight of the atmosphere above, hot as lava, but frozen into crystal lattices at the same time. This exotic interior might explain some of Uranus's strangest properties, but we'll get to that. Let me tell you more about what's happening deep inside this ice giant, because it's one of the most alien environments in the entire solar system. The atmosphere you'd first encounter descending into Uranus is mostly hydrogen and helium, familiar elements similar to Jupiter and Saturn. But as you go deeper, the composition changes. Methane becomes more abundant, then ammonia, then water. The ices that give ice giants their name aren't frozen solid at these depths. They're compressed into hot, dense fluids. At about 100 kilometers below the visible cloud tops, pressure reaches levels that would crush a nuclear submarine like a paper cup. But you've barely scratched the surface. The interesting stuff happens much deeper. At perhaps a quarter of the way to the center, you'd encounter a region where water, ammonia, and methane exist as ionic fluids, molecules broken apart by heat and pressure, their charged fragments conducting electricity like a battery's electrolyte. This conductive layer might be where Uranus's strange magnetic field is generated. Deeper still, perhaps halfway to the center, conditions become truly exotic. Pressure exceeds several million atmospheres, temperature reaches thousands of degrees, and water enters the superionic state I mentioned earlier. In superionic water, oxygen atoms form a rigid crystalline structure, a lattice, like the arrangement of atoms in a solid crystal. But the hydrogen atoms aren't locked in place. They flow through the oxygen lattice like a liquid, carrying electric charge as they move. This creates something unprecedented, a material that's simultaneously solid and liquid, insulator and conductor, crystal and flow. Nothing like it exists naturally on Earth. Scientists only recently created it in laboratory conditions, using powerful lasers to shock compress water samples for fractions of a second. Inside Uranus, this exotic state might persist continuously, forming an ocean thousands of kilometers deep. The implications are staggering. A superionic water ocean would conduct electricity efficiently, potentially generating magnetic fields through mechanisms unlike anything on Earth or Jupiter. And then there's the diamond rain. At extreme pressures and temperatures, Methane molecules, each containing 1 carbon and 4 hydrogens, can be torn apart. The carbon atoms, freed from their hydrogen bonds, would naturally seek each other out, forming new carbon-carbon bonds. Under these conditions, the most stable arrangement of carbon is diamond. Laboratory experiments have shown that when methane is compressed to millions of atmospheres and heated to thousands of degrees, tiny diamonds form and precipitate out of the mixture. They literally rain downward through the surrounding fluid. If this process occurs inside Uranus, diamonds the size of pebbles, maybe even larger, might be falling through the planet's interior like hailstones in a thunderstorm. A perpetual rain of gemstones, thousands of kilometers deep, lasting for billions of years. We can't observe this directly. No probe could survive the journey into Uranus's depths, but the physics strongly suggests it's happening. Somewhere inside that bland blue ball, diamonds are falling like rain. This is the hidden drama of Uranus. On the outside, it looks boring, a featureless blue sphere, the wallflower of the solar system. On the inside, it's a cauldron of exotic physics, superionic oceans, and diamond precipitation. First, let's talk about how we discovered this bizarre world in the first place. Because, unlike every other classical planet, Uranus was found not by ancient astronomers gazing at the sky, but by a musician with a homemade telescope. The date was March 13th, 1781. The location was a garden in Bath, England, and the discoverer was a German-born musician named William Herschel, who had taken up astronomy as a hobby. Herschel was obsessive about his hobby. He built his own telescopes, grinding the mirrors by hand, a process so tedious that his sister Caroline would feed him by placing food in his mouth while he worked. His telescopes were better than anything commercially available, which allowed him to see details that other astronomers missed. His largest telescope, completed in 1789, had a mirror 4 feet across and a tube 40 feet long. For a time, it was the largest telescope in the world. Astronomers came from across Europe to use it, and King George III proudly showed it to visitors. But it was with a much smaller instrument, a telescope with a 6-inch mirror, that Herschel made his most famous discovery. On that March night, Herschel was conducting a systematic survey of the sky, cataloguing every star he could see in certain regions. It was methodical, painstaking work, the astronomical equivalent of counting grains of sand on a beach. And then he saw something that didn't belong. In the constellation Gemini, there was an object that looked different from the stars around it. Stars appear as points of light, even through the best telescopes. This object showed a disk, a tiny circular shape that indicated it was closer than the stars. And over the following nights, it moved against the stellar background. Herschel's first thought was that he had discovered a comet. Comets were known to appear as fuzzy, disk-like objects that moved through the sky. He reported his discovery accordingly. A curious, either nebulous star or perhaps a comet. But as astronomers across Europe tracked the object over the following months, a different picture emerged. Comets follow elongated, eccentric orbits. They swoop in close to the Sun, develop their characteristic tails as ice vaporizes, and then recede back into the outer solar system. Their paths are highly elliptical, stretched ovals that carry them from the inner solar system to beyond Neptune and back. This object was different. Its orbit was nearly circular, and it was far beyond Saturn, at the outer edge of the known solar system. It wasn't a comet. It was a planet. The discovery sent shockwaves through the scientific world. For as long as humans had recorded history, there had been 7 wandering objects in the sky: the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. Ancient civilizations had built calendars around them. Astrologers had attributed mystical significance to them. The 7 days of the week were named after them. And now, suddenly, there was an 8th. The solar system was bigger than anyone had imagined. The discovery made Herschel famous overnight. King George III, a supporter of science and the arts, appointed Herschel as the royal astronomer, with a salary that allowed him to abandon his musical career. For the rest of his life, Herschel devoted himself to astronomy, discovering thousands of nebulae and star clusters, 2 moons of Uranus, 2 moons of Saturn, and infrared radiation from the Sun. But the naming of his planet would prove contentious. Herschel, ever grateful to his royal patron, proposed calling the new world Georgium Sidus, Latin for George's star. He hoped the name would honour the king and cement British prestige in astronomical history. This did not go over well outside Britain. French astronomers, who had just fought a war against King George, refused to use the name. They suggested Herschel instead. German astronomer Johann Bode proposed Uranus, after the Greek god of the sky, the father of Saturn in mythology, maintaining the tradition of naming planets after Roman deities in order of their distance from the Sun. The debate dragged on for decades. British almanacs used Georgian well into the 19th century. But eventually, Uranus won out, becoming universally accepted by the 1850s. And yes, the pronunciation has been causing awkward moments ever since. For the record, astronomers generally prefer Uranus over Uranus. The former is closer to the original Greek. The latter sounds like something you'd discuss with a doctor. But enough about the name. Let's get to what makes this planet truly strange. Let's talk about the tilt. Every planet has what's called an axial tilt, the angle between its rotational axis and a line perpendicular to its orbital plane. Think of it as how much the planet leans as it spins. Earth's tilt is about 23.5 degrees. This modest lean gives us our seasons. In June, the northern hemisphere tilts toward the sun, receiving more direct sunlight, summer. In December, it tilts away, winter. The southern hemisphere experiences the opposite. Most planets have similar modest tilts. Mars is tilted about 25 degrees, very similar to Earth. Saturn is tilted about 27 degrees. Jupiter is barely tilted at all, just 3 degrees from vertical. And then there's Uranus, tilted 98 degrees. Let me help you visualize what this means. Imagine you're looking at the solar system from above, watching the planets orbit the sun like runners on a track. Most planets spin like tops as they orbit, their axes pointing roughly up, perpendicular to the track. They might lean a little, but they're fundamentally upright. Uranus is different. Uranus is lying on its side, rolling along the track like a barrel. Its axis doesn't point up, it points almost directly along the orbital path. One pole faces the sun, then, 42 years later, the other pole faces the sun. Actually, it's even stranger than lying perfectly on its side. Because the tilt exceeds 90 degrees, Uranus technically rotates retrograde, backward compared to most planets. If you could stand on Uranus and watch the sun, it would rise in the west and set in the east. The stars at night would move in the opposite direction from what we see on Earth. This extreme tilt creates seasons unlike anything else in the solar system. Here's what a year on Uranus looks like. Uranus takes 84 Earth years to complete one orbit around the Sun. During this orbit, different parts of the planet face toward and away from the Sun in an extreme cycle. Start at the North Pole. When it's pointed toward the Sun, that pole experiences continuous daylight, not just for a day or a week, but for about 21 years. The Sun rises, spirals slowly up in the sky over years, reaches a maximum elevation, hovers there, then slowly spirals back down over another 20 years before finally setting. Then comes night. 42 years of darkness. No sun at all. Just stars and the dim glow of the ice giant's internal heat. Think about what that means for a human perspective. If you were born at sunrise on Uranus's North Pole, you'd be a middle-aged adult before you saw your first sunset. You'd be an elderly person, if you lived that long, before the sun rose again. The equatorial regions experience something different but equally bizarre. There, day and night cycle rapidly. Uranus rotates every 17 hours, giving the equator relatively normal days and nights. But the path of the sun through the sky changes dramatically over the 84-year orbit. At some points, the sun barely rises above the horizon, circling low around the sky. At other times, it passes nearly overhead. The seasonal changes aren't about hot and cold. The entire planet is frigidly cold, but about how the feeble sunlight is distributed. And here's where it gets really strange. You'd expect the pole that's been in continuous sunlight for 42 years to be warmer than the pole that's been in continuous darkness. Basic thermodynamics, right? More heat in, higher temperature. But when Voyager 2 flew past Uranus in 1986, it found something unexpected. The South Pole, which had been basking in continuous sunlight for decades, was actually slightly cooler than regions that were just emerging from darkness. The planet was somehow redistributing heat in ways that defied simple models. The atmosphere was absorbing energy on the day side and efficiently transporting it to the night side, evening out the temperature across the entire planet. We still don't fully understand how this works. Uranus's atmosphere has tricks we haven't figured out yet. But the real question, the one that has puzzled scientists since we first measured the tilt accurately, is this: how did Uranus get this way? Here's the problem. Planets form from rotating disks of gas and dust around young stars. Everything in the disk rotates in the same direction, spinning around the newborn star like water swirling down a drain. When planets coalesce from this material, they inherit that rotation. They should spin upright, their axes perpendicular to their orbits. Most planets follow this expectation. Their modest tilts can be explained by small gravitational interactions, minor impacts, and the general chaos of the early solar system. A few degrees here or there is normal. But 98 degrees? That requires something dramatic, something violent, something that fundamentally altered the planet's spin after it had already formed. The leading hypothesis is impact. Early in the solar system's history, during a period called the Late Heavy Bombardment, roughly 4 billion years ago, the inner and outer solar system were chaotic places. Giant planets were still migrating, scattering smaller bodies everywhere. Impacts were common, some of them catastrophic. The theory proposes that Uranus, already a fully formed ice giant, was struck by a massive object, perhaps a protoplanet the size of Earth, or even larger. The impact didn't destroy Uranus, but it knocked it over, tilting its axis from near vertical to almost horizontal. The collision would have been apocalyptic beyond imagination. An Earth-sized body hitting Uranus at typical solar system velocities would release energy equivalent to trillions of nuclear weapons detonating simultaneously. The impactor would have been destroyed, vaporized by the energy of the collision. Huge portions of Uranus's atmosphere and interior would have been melted, disrupted, sprayed into space. But Uranus would have survived. Ice giants are remarkably resilient. Their fluid interiors can absorb tremendous impacts without being destroyed. The planet would have gradually re-equilibrated, settling into its new, bizarre orientation. This theory is elegant and matches what we know about the violence of the early solar system. But it has a problem. Let me explain that problem in more detail, because it reveals how much we still don't understand. A massive impact should have left evidence. Specifically, it should have affected Uranus's moons. When a giant impact occurs, it doesn't just tilt the target planet. It ejects enormous amounts of debris into orbit. This debris eventually coalesces into moons. We think this is how Earth's moon formed, from the debris of a Mars-sized body hitting the early Earth about 4.5 billion years ago. The moon-forming impact on Earth left clear signatures. The moon orbits roughly in Earth's equatorial plane. Its composition matches material from Earth's mantle. The angular momentum of the Earth-Moon system tells us about the energy of the original impact. If a similar process tilted Uranus, we should see similar signatures. The debris from the impact should have formed a disk of material around the tilted planet. Moons coalescing from this disk should orbit in a plane related to the impact geometry, not necessarily aligned with Uranus's new equator, but at some angle determined by where the impactor came from. Instead, Uranus's moons orbit almost perfectly in the plane of the planet's equator. All 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, orbit in neat circular paths around Uranus's equator, tilted at the same 98-degree angle as the planet itself. It's as if the entire system formed from a disk that was already tilted, rather than being knocked askew by an impact. The smaller moons follow the same pattern. The rings orbit in the equatorial plane. Everything is aligned with the planet's bizarre tilt, as if it had always been this way. This is very difficult to explain with a single impact. One possibility is that the impact debris disk, over millions of years, was gradually pulled into alignment with Uranus's equator by tidal forces. The gravitational influence of the planet would have tugged at the disk, slowly dragging it into the equatorial plane. Simulations show this can happen, but it requires fine-tuning. The disk has to be the right mass, the right distance from the planet, and the process has to occur over the right timescale. It's possible, but it feels like special pleading. Another hypothesis proposes not one impact, but 2. In this scenario, the first impact tilted Uranus to some intermediate angle, perhaps 40 or 50 degrees. This created a debris disk that began forming moons. Then, millions of years later, a second impact hit from a different direction, adding to the tilt and providing additional debris. 2 impacts could explain the extreme final tilt, while also giving the moon system time to form and align. But 2 giant impacts on the same planet seems like an extraordinary coincidence. The early solar system was violent, yes, but was one planet really unlucky enough to be hit twice by Earth-sized objects? There's a third hypothesis, and it's the strangest of all. What if Uranus was tilted not by an impact, but by a moon? Here's how it would work. Imagine that billions of years ago, Uranus had a large, distant moon, perhaps similar in size to Earth's moon. This moon orbited far from Uranus, near the edge of the planet's gravitational influence. Over millions of years, a complex gravitational dance developed between the Moon, Uranus, and the Sun. This phenomenon, called secular spin-orbit resonance, can gradually tilt a planet's axis through accumulated gravitational tugs. The process would have been slow, happening over tens or hundreds of millions of years. But eventually, it could have tilted Uranus to extreme angles. At some point, the process would have become unstable. The Moon would have been ejected from the system, flung out into the solar system by the same gravitational interactions that had tilted the planet. Or perhaps it spiraled inward and crashed into Uranus, destroyed by the planet it had tilted. Either way, the Moon would be gone. Uranus would be left with its extreme tilt, but no obvious explanation. Like a murder mystery where the weapon has vanished. This hypothesis is elegant and avoids the fine-tuning problems of the impact theories. But it has its own issues. We have no direct evidence such a moon ever existed. The dynamics are complex and not fully understood, and it doesn't easily explain the regular orbits of Uranus's current moons. The truth is, after more than 40 years of study, we still don't know why Uranus is tilted. Every hypothesis has strengths and weaknesses. Every computer simulation matches some observations, but not others. The planet keeps its secret. And that matters beyond just understanding one weird world. Uranus-sized planets are among the most common in the galaxy. When we look at exoplanets, worlds orbiting other stars, we find that ice giants are everywhere. They vastly outnumber gas giants like Jupiter and Earth-like rocky planets alike. Understanding how Uranus got its tilt might tell us something fundamental about how these common planets form and evolve. Are extreme tilts common? Do most ice giants get knocked around in their youth? How does a planet's tilt affect its habitability, its moons, its potential for developing conditions friendly to life? We don't know. And until we study Uranus more closely, sending new spacecraft, making new measurements, we won't know. But the tilt is just the beginning. Let's talk about what's happening inside this planet, because the strangeness goes all the way to the core. I mentioned earlier that Uranus might contain an ocean of superionic water deep in its interior. But that's not the weirdest thing about what's inside. Let's talk about the magnetic field. Because if you thought the axial tilt was strange, this will really bake your noodle. Magnetic fields are invisible, but they're enormously important. They shape how planets interact with the solar wind, the stream of charged particles constantly flowing outward from the sun. They determine whether a planet has auroras. They affect whether an atmosphere can survive over billions of years. Earth's magnetic field is like an invisible shield, deflecting most of the solar wind around our planet. Without it, that stream of radiation would gradually strip away our atmosphere, leaving Earth as barren as Mars. Our magnetic field may be one reason life was able to develop here. So understanding magnetic fields isn't just academic curiosity, it's fundamental to understanding planetary habitability. Earth has a magnetic field generated in its liquid iron core. As the outer core flows, driven by convection from the heat of the inner core, it creates electric currents. These currents generate a magnetic dipole, essentially turning our planet into a giant bar magnet. Earth's magnetic field is roughly aligned with the rotation axis. The magnetic poles are near the geographic poles, offset by only about 11 degrees. This makes sense. The processes generating the field are symmetric around the rotation axis, so the field should be too. Most planets follow this pattern. Jupiter has a powerful magnetic field tilted about 10 degrees from its rotation axis. Saturn's field is almost perfectly aligned, less than 1 degree of tilt. Even distant Neptune, another ice giant, has its magnetic field tilted about 47 degrees. Weird, but not completely crazy. Uranus breaks every rule. Its magnetic field is tilted 59 degrees from the rotation axis. Let me repeat that. 59 degrees. The magnetic pole is closer to the equator than to the geographic pole. If Earth's magnetic field were tilted like Uranus's, compass needles in New York would point towards somewhere in South America. But wait, it gets weirder. Earth's magnetic field is centered on the planet. The dipole runs through the center, from one pole to the other. This is what you'd expect from a field generated uniformly in a spherical core. Uranus's magnetic field isn't centered. The dipole is offset from the planet's center by about 1/3 of Uranus's radius. It's as if the magnetic field is being generated not at the center of the planet, but off to one side. What could possibly cause this? The honest answer is, we're not entirely sure. But the leading hypothesis involves that exotic interior I mentioned earlier, the superionic water ocean. On Earth and Jupiter, magnetic fields are generated deep in the core, where conditions create electrically conductive fluids. For Earth, it's liquid iron. For Jupiter, it's metallic hydrogen. Hydrogen compressed so intensely that electrons flow freely like in a metal. Uranus doesn't have a metallic hydrogen layer. It's not massive enough to compress hydrogen to that state, and its small rocky core isn't hot enough to drive vigorous convection. Instead, the magnetic field might be generated in a shell of electrically conductive fluid, perhaps that's superionic water, or some mixture of water, ammonia, and methane ions, located partway between the core and the cloud tops. If this conductive layer isn't centered on the planet, and if the convection within it is asymmetric, you could get a tilted, offset magnetic field like what we observe. But why would the conductive layer be off-center? Perhaps the giant impact that tilted the planet also disrupted the interior, creating asymmetries that persist to this day. Or perhaps the exotic physics of superionic matter creates patterns we don't yet understand. The magnetic field of Uranus is a puzzle wrapped in a mystery. We've only measured it once, during the Voyager 2 flyby in 1986, and those measurements, while groundbreaking, were limited. We need more data. Let me tell you about that Voyager flyby, because it's the only time we've ever visited this strange world up close. By the time Voyager 2 reached Uranus in January 1986, the spacecraft had already been travelling for 8.5 years. It had passed Jupiter in 1979 and Saturn in 1981, using gravitational assists from each planet to redirect its trajectory toward the outer solar system. The encounter was brief. Voyager flew past Uranus on January 24, 1986, coming within 81,000 kilometers of the cloud tops, close by astronomical standards, but still far enough that the planet appeared as a featureless blue-green ball in the photographs. The images were initially disappointing. Unlike Jupiter with its great red spot and colourful bands, unlike Saturn with its spectacular rings, Uranus looked almost blank. A uniform, hazy blue sphere with barely any visible features. Scientists had expected storms. They had expected dramatic cloud patterns. Jupiter has the great red spot, a storm larger than Earth that has raged for centuries. Saturn has the hexagon, a bizarre six-sided polar vortex, unlike anything else in the solar system. Surely Uranus would have its own dramatic features. Instead, it looked like a billiard ball, smooth, featureless, boring. This apparent blandness was itself interesting. Where were the storms? Where were the cloud bands? Why was Uranus so quiet compared to its neighbours? Part of the answer was the geometry of the encounter. When Voyager arrived, Uranus's south pole was pointed almost directly at the Sun and at Voyager. The spacecraft was looking down at a pole that had been in continuous sunlight for decades, where atmospheric circulation might be fundamentally different from the banded patterns seen on Jupiter and Saturn. When you look at Jupiter or Saturn, you see their equators, the regions where Coriolis forces from the planet's rotation create alternating bands of east-west winds. Uranus, seen pole on, presented a completely different view. The circulation patterns might have been there, but the viewing geometry made them invisible. But part of the answer was genuinely mysterious. Uranus's atmosphere really is less active than the other giant planets. It radiates very little internal heat compared to Jupiter, Saturn, or Neptune. This reduced heat flow means less energy to drive atmospheric circulation, resulting in a calmer, more uniform appearance. Actually, calling Uranus featureless isn't quite fair. Voyager did see subtle cloud patterns, faint bands, small bright spots, hints of circulation. And in the decades since, ground-based telescopes and the Hubble Space Telescope have captured storms, cloud formations, and atmospheric changes as Uranus's seasons slowly evolve. In 2006, a dark spot appeared in Uranus's atmosphere, the first major storm ever observed on the planet from Earth. It was nothing like Jupiter's Great Red Spot, but it proved that Uranus does have weather. It's just subtle, hidden behind that smooth blue haze. More recently, astronomers have observed bright cloud features erupting at mid-latitudes, suggesting convective storms punching up through the atmosphere. As Uranus approaches its next equinox, when the Sun will shine directly on its equator for the first time since 1965, scientists expect atmospheric activity to increase. We might be seeing Uranus during its quiet season. The decades of one-sided heating may suppress circulation. As the heating becomes more even, the atmosphere might wake up.
Why does Uranus have so little internal heat? This is another puzzle. Giant planets are expected to have internal heat left over from their formation. As gas and ice accumulated to form the planet, gravitational potential energy was converted to heat. This primordial heat should leak out slowly over billions of years, driving atmospheric activity and contributing to the planet's energy budget. Jupiter radiates about twice as much energy as it receives from the Sun. Saturn radiates about 2.5 times as much. Even Neptune, similar in size to Uranus and even farther from the Sun, radiates about 2.5 times its solar input. Uranus radiates almost nothing beyond what it receives from the Sun. Its internal heat output is negligible, possibly the lowest of any giant planet. Where did the heat go? One hypothesis points to the giant impact. When an Earth-sized body struck Uranus 4 billion years ago, the collision would have thoroughly stirred the planet's interior, mixing hot material from the core with cooler material from the outer layers. This mixing could have allowed the internal heat to escape more rapidly than in a planet that was never disrupted. In other words, the same impact that tilted Uranus may also have cooled it, draining away the primordial heat that should be driving atmospheric activity today. This is speculative, but it ties together two mysteries, the tilt and the missing heat, into a single coherent story. The impact explains both. But Voyager 2 did more than photograph a bland blue ball. It discovered rings and moons, measured the magnetic field, and observed the faint atmospheric features that do exist. Let's talk about the rings. Yes, Uranus has rings. They're not as spectacular as Saturn's. They're thin, dark, and nearly invisible from Earth. But they exist. And like everything else about Uranus, they're weird. Saturn's rings are famous, bright, broad, and beautiful, visible through even a small telescope. They're made of countless chunks of nearly pure water ice, ranging from dust grains to house-sized blocks, all orbiting in a vast flat disk. Sunlight reflects off this ice, making the rings brilliant and obvious. Uranus's rings are the opposite in almost every way. They're dark, among the darkest objects in the solar system, reflecting only a few % of the light that hits them. While Saturn's rings are icy white, Uranus's rings are charcoal black. They're narrow, typically only a few kilometers wide, separated by gaps thousands of kilometers across. Saturn's rings span hundreds of thousands of kilometers in nearly continuous sheets. Uranus's rings look like cosmic guitar strings, thin lines with vast emptiness between them. And they're hard to see. From Earth, even with the best telescopes, Uranus's rings are a challenge to observe. They were discovered not by direct imaging, but by accident. The discovery happened in March 1977. Astronomers were preparing to observe Uranus as it passed in front of a distant star, a rare event called a stellar occultation. By watching exactly when the star disappeared behind Uranus and reappeared on the other side, they could precisely measure the planet's size and atmospheric properties. James Elliott, Edward Dunham, and Douglas Mink were observing from the Kuiper Airborne Observatory, a modified aircraft carrying a telescope high above the clouds for clearer viewing. Other teams were observing from ground-based telescopes around the world. But as they watched, something unexpected happened. Before Uranus itself blocked the starlight flickered. It dimmed briefly, then returned to full brightness, then dimmed again. 5 distinct dips, each lasting only seconds. And after Uranus passed and the star reappeared, the same pattern repeated in reverse. 5 more dips on the other side. The symmetry was the key. Whatever had caused the dips on the way in was also present on the way out, at exactly the same distances from the planet. Something was orbiting Uranus. Something thin enough to let most of the starlight through, but dense enough to partially block it. Rings. The announcement shocked the astronomical community. Rings around Uranus. No one had predicted them. No one had seen any hint of them through centuries of telescope observations. Further occultation observations confirmed at least 9 distinct rings, later increased to 13 by Voyager 2 and subsequent observations. The rings are made of extremely dark material, among the darkest in the solar system, reflecting only a few % of the light that hits them. This explains why they escape detection for so long. What keeps these rings so narrow? Ring particles should spread out over time due to collisions and gravitational interactions. Saturn's broad rings may represent a relatively recent formation, still in the process of spreading. Uranus's narrow rings suggest something is actively confining them. The answer is shepherd moons. small satellites whose gravitational influence herds the ring particles into narrow bands. Voyager 2 discovered several of these tiny moons embedded in or near the ring system. And then there's the orientation of the rings. Like Uranus's moons, the rings orbit in the plane of the planet's equator, tilted 98 degrees from the orbital plane. Looking at Uranus from Earth, the rings appear nearly vertical, standing on end rather than lying flat like Saturn's. When Voyager 2 arrived in 1986, the rings were seen nearly edge-on, making them very difficult to observe. In the decades since, as Uranus has moved along its orbit and the viewing geometry has changed, we've been able to see the rings more fully. In 2007, Earth passed through the plane of Uranus's rings, giving us an edge-on view similar to what Voyager saw. But by 2017, the rings were tilted far enough for detailed observation, and new images from large ground-based telescopes have revealed additional faint rings and structures. The rings remain mysterious. We don't know exactly how old they are, what they're made of, or how they formed. They might be ancient, dating back to the early solar system, or they might be relatively young, created by the disruption of a captured comet or asteroid. The dark material is unusual, possibly organic compounds processed by radiation over billions of years, or perhaps primordial material from the outer solar system that never accumulated into larger bodies. Like so much about Uranus, the rings raise more questions than they answer. Now let's talk about the moons. Because Uranus has 27 known moons, and several of them are among the strangest objects in the solar system. The naming convention for Uranus's moons is unique in the solar system. While other planets' moons are named after figures from Greek and Roman mythology, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. This tradition began with the first 4 moons discovered and has continued ever since. So we have moons named Oberon and Titania, the fairy king and queen from A Midsummer Night's Dream, Ariel and Miranda from The Tempest, Puck, the mischievous sprite, Juliet and Desdemona and Ophelia. It's as if the solar system decided to host an English literature class. The 5 major moons, Miranda, Ariel, Umbriel, Titania and Oberon, were all known before the space age. Titania and Oberon were discovered by Herschel himself in 1787, just 6 years after he discovered the planet. Ariel and Umbriel were found in 1851 by William Lassell. Miranda was discovered in 1948 by Gerard Kuiper. All 5 orbit in the plane of Uranus's equator, meaning they share the planet's extreme tilt. When one pole of Uranus points toward the Sun, these moons orbit in circles around that pole like electrons around an atomic nucleus. The orbital periods range from about 1.5 Earth days for Miranda, the innermost major moon, to about 13.5 days for Oberon, the outermost. All 5 are tidally locked, meaning they always keep the same face toward Uranus, just as our moon always keeps the same face toward Earth. Voyager 2 photographed all 5, revealing diverse worlds with distinct personalities. But one moon stood out as uniquely bizarre: Miranda. Miranda is the smallest of the 5 major moons, only about 470 kilometers in diameter, small enough that you could drive across it in a few hours if you had a car and a road. Its surface gravity is so weak that you could easily jump over a 3-story building. A baseball thrown hard enough would escape into space. But what Miranda lacks in size it makes up for in strangeness. The surface of Miranda looks like it was assembled from spare parts by a cosmic Dr. Frankenstein. There are ancient, heavily cratered regions that look billions of years old. Surfaces that have been accumulating impact scars since the dawn of the solar system. These regions are what planetary scientists expected to see on a small, cold moon. And then, right next to them, there are young, grooved terrains that look like nothing else in the solar system. These features are called coronae, large, roughly rectangular or oval regions marked by concentric grooves and ridges. From above, they look like someone pressed a giant rectangular cookie cutter into the moon's surface and then scratched it with a fork. 3 major coronae dominate Miranda's surface: Arden corona, Elsinore corona, and Inverness corona, named after locations in Shakespeare's plays. Each is roughly 200 to 300 kilometers across, comparable in size to medium-sized countries on Earth. The boundaries between the coronae and the ancient crater terrain are sharp and dramatic. It's as if someone took chunks from different moons and glued them together without any attempt to smooth the seams. The most famous feature on Miranda is Verona Rupes, a cliff located at the edge of one of the coronae. This cliff is roughly 20 kilometers high, the tallest known cliff in the solar system. For comparison, Mount Everest is about 9 kilometers above sea level. If you stood at the top of Verona Rupes and dropped a rock, it would fall for about 12 minutes before hitting the bottom. Miranda's gravity is so weak, about 1/80th of Earth's, that the rock would accelerate slowly, never exceeding about 200 kilometers per hour before impact. If you jumped off Verona Rupes, you might actually survive. The terminal velocity in Miranda's negligible gravity would be low enough that you'd hit the ground at roughly the speed of a skydiver landing with a parachute on Earth. It would hurt, and you'd probably break some bones, but it wouldn't necessarily be fatal. Of course, you'd have died of exposure to vacuum long before you reached the bottom, so the physics of the fall is academic. How did Miranda get this way? One early hypothesis suggested that Miranda was shattered by a giant impact and then gravitationally reassembled. The various terrain types would represent different chunks of the original moon that came back together in random arrangements. This dramatic idea has fallen out of favour. Current thinking suggests that the coronae formed through internal geological processes, perhaps upwelling of warm ice from the interior, driven by tidal heating from Uranus's gravity. Miranda might have passed through orbital resonances with other moons in the past, when gravitational interactions pumped energy into the little moon, heating its interior and driving the strange geology we see today. But the truth is, we don't fully understand Miranda. Like so much about the Uranus system, it demands closer study. The other major moons are less dramatically strange, but still fascinating. Titania and Oberon, the largest moons, are about 1,500 kilometers in diameter, roughly half the size of Earth's moon. If you could stand on either one, Uranus would dominate the sky. A massive blue-green disk, far larger than the full moon, appears from Earth. Titania shows signs of past geological activity. Enormous canyons slice across its surface, some of them over 1,000 kilometers long. These canyons probably formed when Titania's interior cooled and contracted, cracking the outer crust like the skin of a dried-out apple. Bright patches suggest relatively fresh ice, perhaps exposed by more recent impacts. Oberon is more heavily cratered, its surface looking ancient and battered. But even Oberon shows signs of geological history.
Dark patches on crater floors suggest cryovolcanism, where water or water-ammonia mixtures erupted onto the surface from below, then froze into dark ice. These two large moons might harbour subsurface oceans. The tidal forces from Uranus are weak at their distance, but radioactive decay in their rocky cores could provide enough heat to maintain liquid water deep underground. We won't know without sending a spacecraft to investigate, and that's one of the key science goals of the proposed Uranus mission. Aerial shows the youngest surface of the major moons, with bright, fresh terrain and relatively few craters in some areas. Something has been resurfacing Aerial more recently than the other moons, perhaps cryovolcanic activity driven by tidal heating. Aerial might still be geologically active today, though we have no way to confirm this with current data. The surface of Aerial is crossed by enormous valleys, some of them partially filled with smooth material that looks like frozen floods. Water or ammonia mixtures might have erupted from below, flowed across the surface, and frozen in place. If this is still happening, Aerial could have a subsurface ocean, making it a potential target in the search for habitable environments in the outer solar system. Umbriel is the darkest of the major moons, its surface coated with material that reflects very little light. This gives Umbriel a mysterious, shadowy appearance, as if it's been dipped in cosmic soot. One bright ring, called Wunda, stands out near Umbriel's equator, a circular feature about 130 kilometers across that might be a crater filled with bright ice or frost. Against the dark background of Umbriel's surface, Wunda shines like a spotlight. Why is Umbriel so dark? The surface material might be ancient, processed by billions of years of radiation into carbon-rich compounds that absorb light. Or it might have been coated by dark debris from elsewhere in the Uranian system. We don't know. Beyond the 5 major moons, Uranus has 22 smaller satellites. Some, like Puck, are a few hundred kilometers across and were photographed by Voyager 2. Others are tiny, only a few kilometers in diameter, discovered from Earth using modern telescopes. The innermost small moons orbit among the rings, shepherding ring particles and creating gaps. The outermost moons have a peculiarity. Several of them orbit retrograde, backward compared to the inner moons and the planet's rotation. These outer retrograde moons were probably captured from the outer solar system, asteroids or Kuiper belt objects that wandered too close to Uranus and became trapped in its gravity. Their orbits are tilted, eccentric and chaotic, nothing like the orderly inner system. The contrast is striking. The inner moons, including all 5 major ones, orbit in neat circles aligned with Uranus's equator. The outer moons orbit in every direction at random angles, some forward and some backward. It's as if the Uranian system has 2 populations of moons, a native population that forms with the planet, and an immigrant population captured later from interstellar space. The moon system of Uranus is a complex laboratory for understanding planetary formation and evolution, but like the planet itself, it remains poorly explored. Let me paint a picture of what Uranus might look like if you could actually visit. Imagine approaching from deep space, having travelled for years from Earth. At first, Uranus is just a point of light, brighter than the surrounding stars, but unremarkable. As you draw closer over weeks and months, it gradually resolves into a disk, pale blue-green, the colour of a faded swimming pool. Approach from space,
and the planet initially appears as a blue-green marble, almost featureless. As you get closer, faint cloud bands emerge, barely visible zones and belts, much more subtle than Jupiter's dramatic stripes. The colour comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green. The rings would be visible now, thin, dark lines encircling the planet at strange angles. From your approach trajectory, they might appear as a halo or as an ellipse, depending on your angle. Unlike Saturn's brilliant white rings, these are dark as charcoal, barely reflecting any light. Moons would dot the space around Uranus, tiny points of light at first, then gradually resolving into spheres as you approached. Miranda, the closest of the major moons, would show its patchwork surface of coronae and cratered terrain. Ariel and Umbriel would gleam with reflected light. Distant Titania and Oberon would be smaller, farther, but still visible. As you descended into the atmosphere, you would experience increasing pressure and changing conditions. The upper atmosphere is hydrogen and helium, cold and thin, colder than liquid nitrogen, nearly as cold as deep space itself. The blue colour would deepen around you as you sank into the methane haze. Below that is a layer of methane, ammonia, and hydrogen sulfide clouds. If you could smell it, which you couldn't because you'd be dead from the cold and the pressure and the lack of oxygen, it would smell like rotten eggs. Ammonia would add a sharp, acrid note. It would be thoroughly unpleasant even before it killed you. Keep descending and the pressure builds. What felt like vacuum at the cloud tops now feels like the bottom of the ocean, then like something beyond any ocean on Earth. The hydrogen around you transitions from gas to something between liquid and gas, a supercritical fluid that's neither one thing nor the other. The ices, water, ammonia, methane, become increasingly compressed and hot despite the planet's cold exterior. You'd experience a strange inversion. The deeper you go, the hotter it gets. The surface is frigid, the interior is thousands of degrees. At some depth, we're not entirely sure where, you might encounter the superionic water ocean. Thousands of kilometers deep, composed of matter that exists nowhere else in the solar system, except possibly inside Neptune. The oxygen atoms locked in crystal lattices, the hydrogen atoms flowing like water. Diamonds precipitating out of the methane, raining downward toward the core. No spacecraft could survive this journey. The pressures would crush any material we know how to build. The temperatures would melt any probe. We can only imagine what it looks like, based on physics and calculations, a realm forever beyond direct observation. At the very center lies a small rocky core, perhaps 1 to 2 Earth masses, composed of silicate rock and iron. This core is a remnant of the rocky planetesimal that served as the seed for Uranus's formation 4.5 billion years ago. It's the original kernel around which all that ice and gas accumulated. If you approach from the night side during Uranus's winter solstice, you would see 42 years of accumulated darkness. No sunlight at all, just stars and the cold glow of the planet's internal heat, which, as we discussed, is puzzlingly weak. The darkness would be profound, deeper than any night on Earth. Faint auroras might shimmer around the magnetic poles, shifted far from the geographic poles by the offset magnetic field. Unlike Earth's auroras, which form rings around the polar regions, Uranus's auroras would appear at strange latitudes, twisted and distorted by the tilted magnetic field. The rings would appear edge-on from Uranus's equator, thin, dark lines against the starfield, barely visible. The moons would march in stately procession, circling the tilted equator, their phases changing as they caught light from the distant sun. It would be beautiful, alien, cold beyond imagination, and utterly unlike anywhere else in the solar system. Let me bring this back to why any of this matters. Uranus is not just a curiosity. It's a key to understanding planetary formation throughout the universe. When astronomers discovered the first exoplanets in the 1990s, they expected to find solar systems like our own, small, rocky planets near the star, gas giants farther out. Instead, they found chaos. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. Super-Earths, planets with no analogue in our solar system. Eccentric orbits, tilted orbits, planets orbiting in the opposite direction from their star's rotation. And the most common type of planet? Ice giants. Worlds the size of Uranus and Neptune are everywhere, vastly more common than both gas giants and Earth-like rocky planets. Our solar system, it turns out, is the weird one. Not because it has an ice giant lying on its side, but because it has so few ice giants total. Most planetary systems have multiple Uranus-sized worlds. We have only 2. This discovery has profound implications. For decades, we assumed our solar system was typical. 4 small rocky planets close to the Sun, 4 large planets farther out, with a neat dividing line between them. We expected other solar systems to follow the same pattern. They don't, not even close. Some systems have giant planets orbiting closer to their stars than Mercury orbits the Sun. Some have super-Earths, planets larger than Earth but smaller than Neptune, crammed into tight orbital configurations. Some have ice giants galore, 5 or 6 Uranus-sized worlds where we have just 2. Understanding Uranus, why it's tilted, why it's cold, how its moons and rings formed, might tell us about planetary evolution throughout the cosmos. The same processes that shaped Uranus probably shaped billions of similar worlds around other stars. If giant impacts commonly tilt ice giants, then extreme axial tilts might be normal. This affects seasons, climate, and potentially habitability for any moons. If ice giant interiors commonly produce offset, tilted magnetic fields, that affects how these planets interact with their stellar winds and cosmic radiation. Magnetic fields protect atmospheres and surfaces from erosion. Weird magnetic fields might mean weird atmospheric evolution. If ice giants commonly have strange, dark ring systems and families of quirky moons, that's the norm for planetary systems, and our familiar Saturn-style rings might be the exception. We won't know until we look more closely, and that means going back. The last and only spacecraft to visit Uranus was Voyager 2, more than 37 years ago. The flyby lasted hours. The data was limited by the technology of the 1970s. We learned a tremendous amount, but we barely scratched the surface. Planetary scientists have been advocating for a dedicated Uranus mission for decades. In the 2022 Planetary Science Decadal Survey, a once-a-decade document that prioritizes future exploration, a Uranus orbiter and probe was ranked as the highest priority flagship mission. This was a huge deal. The Decadal Survey is how the planetary science community tells NASA what to build next. Previous Decadal surveys recommended the Mars rovers, the Europa Clipper mission, and the James Webb Space Telescope. Being named the top priority flagship is a significant endorsement. The proposed mission, sometimes called the Uranus Orbiter and Probe, or UOP, would be the first dedicated mission to an ice giant. It would transform our understanding of these common but mysterious worlds. Here's what such a mission might look like. Launch would occur in the early 2030s, taking advantage of a favorable alignment that allows a gravity assist from Jupiter. Without Jupiter's help, the journey to Uranus would take much longer and require much more fuel. With Jupiter's gravity, the spacecraft could slingshot toward the outer solar system, arriving at Uranus about 13 years after launch. That means a mission launching in 2032 would arrive around 2045. An entire generation of planetary scientists would build their careers around this mission, just as previous generations built careers around Voyager, Galileo, and Cassini. Upon arrival, the spacecraft would fire its engines to slow down and enter orbit around Uranus. Unlike Voyager's brief flyby, this mission would stay for years, watching the planet through different seasons, mapping its magnetic field from multiple angles, and making repeated close passes to the moons. The orbiter would carry a suite of sophisticated instruments. High-resolution cameras would photograph the atmosphere in detail, revealing cloud structures and storm systems invisible to Voyager's 1970s technology. Spectrometers would analyze the composition of the atmosphere, rings, and moon surfaces. Magnetometers would map the bizarre magnetic field in 3 dimensions. Particle detectors would study the radiation environment. But the most exciting part might be the atmospheric probe. Like the Galileo probe that plunged into Jupiter in 1995, the Uranus probe would separate from the orbiter and dive into the planet's atmosphere. Protected by a heat shield, it would descend through the cloud layers, directly measuring temperature, pressure, composition, and wind speed. For perhaps an hour, the probe would transmit data back to the orbiter as it fell deeper and deeper into Uranus's atmosphere. Eventually, the pressure and temperature would exceed the probe's design limits, and transmission would cease. But in that hour, we would learn more about Uranus's atmosphere than in all previous observations combined. We would finally know what's really down there. Not just theories and models, but direct measurements. The composition of the cloud layers, the depth of the methane haze, the temperature profile from the stratosphere to the deep atmosphere. Maybe even hints about what lies deeper, the exotic superionic ocean, the diamond rain, the mysteries of the interior. The mission would also make detailed studies of the moons. Multiple flybys of the major moons would reveal their surfaces in unprecedented detail. We might discover whether any of them have subsurface oceans, like the icy moons of Jupiter and Saturn. We might find active geology, or ancient surfaces that record the history of the outer solar system. Miranda, with its bizarre patchwork terrain, would be a prime target. Close flybys could reveal whether the coronae are ancient features or signs of recent geological activity. We might finally understand how this tiny moon became so strange. The rings would be mapped in detail, revealing their structure, composition, and dynamics. We might discover new moons embedded in the rings, new ring arcs, new features invisible from Earth's distance. Such a mission is technically feasible. It could launch in the early 2030s, arriving at Uranus in the mid-2040s. The technology exists. The science case is compelling. The planetary science community has spoken clearly about its priority. Whether it happens depends on funding, priorities, and political will.
Space agencies have many demands and limited budgets. Mars rovers, lunar missions, asteroid explorers all compete for the same resources. But if we want to understand ice giants, and ice giants are the most common type of planet in the galaxy, we need to study the ones in our own backyard. Uranus and Neptune are right here, close enough to reach, strange enough to surprise us. The mysteries are waiting. The only question is whether we'll go solve them. Let me leave you with one final thought. Uranus has been rolling through space for 4 billion years, keeping its secrets. It formed in the chaos of the early solar system, suffered impacts that would have destroyed lesser worlds, and emerged as a tilted, cold, strange ice giant, unlike anything else in our cosmic neighborhood. For most of human history, we didn't even know it existed. It was just another faint point of light, lost among the thousands of stars visible on a dark night. Then William Herschel pointed his homemade telescope at the sky and noticed something odd. A disk instead of a point. Movement against the stars. A planet. In the 2 centuries since, we've learned that Uranus is one of the strangest objects we've ever encountered. A planet tilted on its side. A magnetic field that makes no sense. Moons with canyon cliffs higher than any mountain on Earth. Rings so dark they're nearly invisible. We've learned all this from a single flyby and centuries of telescope observations. Imagine what we could learn with a dedicated mission. Imagine what secrets Uranus might still be hiding. The universe is full of worlds like Uranus, ice giants, tilted and strange, orbiting distant stars. By understanding this one, we might understand billions. That's why Uranus matters, not just as a curiosity in our own backyard, but as a key to the cosmos. The next time you look at the night sky, remember, there's a planet out there rolling on its side, keeping secrets we've barely begun to uncover, and it's waiting for us to come back. You don't need a spacecraft to observe Uranus yourself. On a dark night, far from city lights, Uranus is actually visible to the naked eye, just barely. At magnitude 5.7, it hovers at the edge of human perception, a faint point of light indistinguishable from the thousands of stars around it. With binoculars, Uranus becomes easy to spot if you know where to look. It shows as a star-like point, perhaps with a very slight blue-green tinge that distinguishes it from the white of true stars. Through a small telescope, you can see its tiny disk, just a few arc-seconds across, but definitely not a point. There's something profound about seeing Uranus with your own eyes. The photons hitting your retina travelled for nearly 3 hours from the 7th planet. You're looking backward in time, seeing the planet as it was, not as it is. And somewhere out there, in that faint blue-green glow, diamonds are raining through an ocean of exotic ice. A magnetic field is tilting at impossible angles. 27 moons circle a world that rolls through space on its side. Rings darker than charcoal stand on end. All because something catastrophic happened 4 billion years ago, something we still don't fully understand. That's the beauty of planetary science. Every answer leads to more questions. Every discovery reveals new mysteries. The more we learn, the more we realize how much remains unknown. Uranus has been rolling through space since before life existed on Earth, keeping its secrets, waiting for curious minds to come looking. Maybe those minds will be ours. Thank you for watching. If this video changed how you think about the solar system, consider subscribing. We explore the strangest, most fascinating questions about the universe and our place in it. The cosmos is vast and full of mysteries. Let's explore them together. Remember, somewhere out there, at this very moment, Uranus is rolling through space on its side, just as it has for 4 billion years. Its strange magnetic field is twisting through space. Its dark rings are circling at impossible angles. Its 27 moons are dancing in orbits aligned with a tilt that shouldn't exist. Diamonds are raining through an ocean of superionic ice. Seasons lasting 42 years are slowly cycling. Secrets are waiting to be discovered. And a single spacecraft visited once, 37 years ago, for just a few hours. There's so much more to learn, so much more to discover. And the strangest planet in the solar system is right there, waiting. See you in the stars.